All right, so let's finish up our last section for the week, which is on section 3.2. Okay, and this section is really divided into 3 parts that are all kind of related. Continuity, intermediate value, and end behavior. They're all pretty straightforward concepts. I don't think there's anything here that's overly challenging. All right. First thing is, whenever we try to graph something on the calculator, most of the older calculators assume what you want to draw is connected. So if you're trying to draw something that should not be connected, calculators usually have a hard time with that. Okay. Here's an example of a graph that some calculators would have trouble with. And let me make this look a little better. Okay, it's called a tangent function. Okay? It's just an example of a graph that's not connected. That's all. Right? If I use an older calculator to draw it, sometimes, depending on how we type it in, it doesn't quite look right. Let's try this one first. There we go. See how it's drawing those vertical lines in? Those shouldn't be there. But the calculator has trouble drawing something that, it's like if you were on paper, you'd be picking up your pencil right now and starting a new curve. Older calculators couldn't do that. The newer ones tend to draw them just fine. Okay. Right, so let me try graphing this one. Okay, 1 divided by x minus 3. Okay, we should expect something strange to be happening at 3 because you can't plug 3 in for x. Otherwise, you'd be dividing by 0. That's exactly how that graph should look. Okay, it's not a connected graph. If I were to try to draw it on that other calculator, it would put a vertical line in right there. It would connect them, okay, but it shouldn't be connected. All right, so could you trace this graph with a pencil without picking it up? No. You'd have to trace this part. And then how are you going to get to that other part without picking up your pencil? You have to. And then you could trace the other part. Okay, so this one is no. Okay, let's look at this one. This is called the integer function. Okay, again, not something you have to know how to graph. It's just an example. I want to show you what it looks like. It's under math, number, int. It's going to look like a series of steps. It's called the integer function. And if you were graphing this on an older calculator, it would try to connect each one of them. It actually would look like steps. All right? Could you trace this graph without picking up your pencil? No. But it's for a different reason. It's not because we have a divide by 0 error here. This is a totally different graph. It has breaks in it. It just has these breaks, okay, where this one has a divide by 0 error. So it's 2 different reasons why we can't trace it. And then how about something like this? This would be a parabola. Could you trace that without picking up your pencil? Yeah. Okay, so that one's a little different. Right? So we're going to talk about what it means to be continuous. Okay, or continuity. Okay, very simple. Continuity just means, can you draw what I'm asking you to draw without lifting your pencil? If you can, it's continuous. If you can't, it's discontinuous. Okay, and sometimes I might not ask you to trace the whole graph. Say I gave you something like this and something like this. And I said, over the interval from 2 to 4, could I trace this graph on the interval from 2 to 4 without picking up my pencil? Yeah, just from 2 to 4, that's it. Yeah, we could. Here's 2, here's 4. So in that particular interval, my graph is continuous. Okay? Because I can trace it over the two numbers that I asked without lifting my pencil. Now, there might be other numbers, like if I said trace from -1 to 4. No. You cannot trace from here to here without lifting your pencil. Okay? So in that interval, you'd have to pick it up. It would be discontinuous. All right? So if you have an interval and you have to pick up your pencil to trace, that's called a discontinuous interval. Okay, so usually if you make an interval small enough, it would be continuous. Okay, even for this step function. Okay, if I pick a small enough interval, I could trace without lifting my pencil. But if I make the interval too big, I'd have to skip up to the next step, which would involve lifting my pencil, which would mean that interval is discontinuous. Okay, any questions on that? Yep.
On the older calculators, are you able to at least like trace and it'll like skip a line?
Oh yeah, you can trace, and
So like,
yeah.
it's still possible to like do the homework.
Oh yeah, it'll skip up. It'll do just what this one's doing.
Okay.
Yeah, it'll trace.
It just may be a little confusing.
Yeah, you're just gonna see. You're gonna see it connected. In fact, I could make this one connected too by turning off detect asymptotes. If I turn this off, it would connect all those steps.
Okay.
Yep. So I just mentioned this idea to you. On some graphs, it's possible you could pick some intervals that are continuous and some intervals that are discontinuous. Right, and we're going to do that in this example. Okay, I'm going to type this graph into the calculator. And I want to write down two intervals that I could trace between without picking up my pencil, and two intervals that I couldn't. And there's millions of answers, infinitely many answers here. Okay, when I graph this, what number is this graph going to do something funny at? When x is what? 0. When x is 0, all of a sudden we're going to have a divide by 0 error. A lot of times that results in a discontinuity error. In other words, having to pick up your pencil to get to the next part. All right, so let's graph 1 over x. Okay, so there's the graph of 1 over x. And let's start with two intervals that are continuous. Okay. Anybody give me an interval that I could stop at, trace between the two without lifting my pencil? Yep.
Can you just scroll up to the last line?
Yeah, Whoopi?
3 and 2.
Yeah, between 2 and 3. That's perfect. I can definitely trace between 2 and 3 without lifting my pencil. And it doesn't even matter if you do bracket or parenthesis. That's a very small difference. You can trace between 2 and 3.
So can you do it 5 and 6?
Yeah, you can do 5 and 6. You could do 6 to 10. You could do 5.2 to 5.7. Okay, any of those intervals, you could do negative 9 to negative 10. Those are all continuous intervals. There's just one number you don't want to go through to be continuous. Now we're going to use that for discontinuous. Somebody give me an interval that I could not trace.
-1, 0.
Well, 0 is undefined. So let's just go beyond 0.
-1 to 1.
Yeah, -1 to 1. Any interval that goes through 0, you cannot trace. Okay, anybody give me one more? -2 to 3. Yep. You cannot trace from here to here without lifting your pencil. Okay. So any questions on continuous versus discontinuous intervals? Okay. Don't worry about it. We're not going to do that one. I'm going to skip that one. All right, there's a few different reasons why a function can be discontinuous. Okay, one reason is basically you have a divide by zero error. All right? Your function is not defined at the value you picked. Like this one. If I try to plug in 0 for x, it's undefined. So there's a discontinuity at 0. Okay, another one is not because of a discontinuity, but because of a break in the graph, like the integer function. Okay, basically what the integer function does, kind of simply, is it rounds your number off. All right? So that's why you get these steps. And with the integer function, you can plug any number you want into the integer function. Okay, we haven't talked a lot about it. But let me just type in integer function. Okay, if I go to my table, you can plug in anything you want. Plug in 0, plug in decimals. Basically, it like rounds the number down. That's what the integer function does. 2.5. Negative 3.8 or negative 3.58, 0. Okay, I can plug any number I want into the integer function. So it's not discontinuous because I have a divide by 0 problem. It's discontinuous because of the way it rounds. It gets rid of decimals. Okay, so we call that a break. There's breaks in the graph. Okay. And the other one, the one that's kind of tricky, is a hole. Okay, you can have a small hole in the graph. And with a hole, you can't see it. You have to know it's there using algebra. Okay, this is one thing the calculator cannot do. Right? Let's graph this and see what happens. So x squared plus 3x plus 2. X squared plus 3x plus 2 divided by x minus 2. Or x plus 2. Now, you might be thinking, well, wait, isn't this just a divide by 0 error? If you plug negative 2 in, negative 2 plus 2 is 0, you divide by 0. Yes, it's a divide by 0, but it's not going to look like that. It's going to look like one connected graph. Okay, let me show you. Now, if you try to trace to negative 2, okay, you will have a problem. It won't give you a y value. When x is negative 2, y doesn't exist. But it's not quite the same as the top one. I can go very close to negative 2, like negative 2.00001. That's fine. I could also go negative 1.999. That's fine. But I just can't use negative 2, that one small number. So it's a hole, but it's so tiny. It's infinitely small, right? Very, very, very small. And you can zoom in, but you won't ever see it. And the reason why there's a hole is because watch what happens if I factor the top. It factors into x plus 1. And what's the other factor? X plus 2. Look what happened in the bottom, x plus 2. So basically what this looks like, if I were to graph y equals x plus 1, these two graphs would be almost the same. The only difference between them is the one in blue had a very, very, very small hole at negative 2. The one in red doesn't have that hole. All right, so you get a hole in a graph whenever you can factor the numerator and one of the factors in the top matches what's in the bottom. Okay, if I change the bottom to x plus 3, just change it from a 2 to a 3, totally changes how the graph looks. So let me just show you the difference. There's not going to be a hole in the graph anymore. Because x plus 3 is not a factor in the top. So just changing one number, totally different. Okay. Yeah. So we'll talk more about that. But these are the three reasons why you could have a discontinuity. Okay. Discontinuity where it's like this shape. Okay. You could have that integer function where you have breaks. Or you could have a small hole in the graph. Okay? If you just showed somebody a picture of that on the calculator, they'd never be able to know there's a hole there. Only way you'd know is if you show them this formula and if they knew how to factor. You can't see a hole graphing it on the screen. Okay, one nice thing about polynomials are they are continuous forever. Every single polynomial is a continuous function. They twist and they turn, but you never pick your pencil up to draw them. Okay, think of parabolas, think of cubics, quartics. You never have to pick your pencil up to draw them. So it is impossible to find a discontinuous interval for a polynomial. They are continuous forever. Okay. And if a function is continuous all of the time, it's impossible to find any holes, breaks, or undefined values. It's called a continuous function. Okay. Continuous function, you can draw it without picking up your pencil. No holes, no breaks, no undefined values.
No red light. No red light. No red light.
Yes. Yeah.
So like, if it's a parabola, how can it be all values? Like, if the y, so like minimum was -2, how is that? Like,
So continuous just means I can draw it without ever lifting my pencil. That's all continuous means. Doesn't mean it goes up and down forever. It just means you can sketch it without lifting your pencil. Yep. All right, so that's the first part, okay, continuity. Second part of the lesson, we're going to tie in continuity with what's called intermediate value. Okay, basically, very simple way to describe that. Let's say you had a pot of water, and you measured the temperature of it. It's at 60 degrees. Okay? And then you start heating it. You're going to heat it all the way to boiling. Okay, 212 degrees. So if it starts at 60 and it ends at 212, is the water going to be 90 degrees at some point as you're heating it? How about 106 degrees? Does it skip any temperatures between 60 and boiling? No, boiling is a continuous process. Right? It goes through every single possible temperature between where the water starts at and 212. Even 196.41398 degrees. It'll hit that temperature maybe for a millisecond, and then it keeps heating up. Right? That's the idea of the intermediate value property. Right? So to tie this in with the boiling, right? If you're doing some kind of process that's continuous, like boiling water, and it starts at a certain temperature, stops at a certain temperature, then it's going to go through every single temperature between those two temperatures, where it started and where it stopped. But this depends on it being continuous. If you have a function that's discontinuous, it's possible you skip values, like the step function. You skip all kinds of values. All right? So here's another example. If I have a function that starts here and ends here, I don't care how it gets from there to there. It's going to go through every single possible y value between here and here. Let's say it started at a height of 0 and it ends at a height of 10. It will go through every height between 0 and 10. 1, 2, 3. Maybe it'll go through them a couple times. Maybe this is like 3. It'll hit a height of 3 several times. But I guarantee it'll go through 0 and 10 at least one time. Even if you just drew it as a straight line, it would go through every height between 0 and 10. Okay, any question on that? Does everybody see why this wouldn't work if it was discontinuous? Okay, if I had a function that was like this and said, well, do I go through every height? No. I skip a whole bunch right in here because I picked my pencil up to draw that. All right, so let me show you an example we can do with that. let f of x equal 3x minus 4. This is a line. This is continuous. Slope of 3, y-intercept at negative 4. Okay, what I'm going to try to do is find a value, okay, on this graph so that when I plug in a number for x, I get 15 for y. Well, first, I want to see if that's even possible. Let's figure out where we're starting on the y-axis and where we're ending. If we start below 15 and we end above 15, then I guarantee we'll go through 15 at some point. But let's see if that even happens. Okay, so remember, these are x values. This is an interval, just like you've been doing in the homework, from negative 10 to 10. So what could I do with negative 10 to find out where that is on the y-axis? Yep. Yeah, let's just plug it in. Let's hope we start below negative 15 and we end above 15. And then we go through it in the middle somewhere. All right, so f of negative 10, that's 3 times negative 10, minus 4. That's negative 30, minus 4. So we are starting at negative 34 on the y-axis. That's the lowest we're ever going to go. Now let's find the highest. If it's above 15, we're good. Okay, we'll go through 15 at some point. So f of 10, 3 times 10 is 30. And what's 30 minus 4? 26. So we're starting at negative 34. We're going to end at 26. Do we go through 15 at some point?
Yeah.
We have to, yeah. It's like, think of a temperature at negative 34 warming up to 26. You're going to go through 15 degrees at some point. All right? So that's my y value. So replace the left-hand side with 15. Solve for x. Figure out what value of x you would plug in for, and that would make y 15. Oops, that's x. Trying to find what value of x I would plug in and get 15 for y. So first thing I'd do is add 4 to both sides. And what's my last step? Divide by 3. That's it. If you plug in 19 over 3, which is 6.33, which is exactly between the two numbers we said to be between, and we knew it would be, you will get 15 for y. Now, if I said to you, find a number between negative 10 and 10 so that I get negative 200 for y, am I going to go through negative 200 on this interval? No. Maybe a different interval, but not negative 10 to 10. These are the numbers I go through on the y-axis, negative 10 to 10. Okay? Questions on that? Mm-hmm.
So why did you have to actually plug in the negative 10 and 10?
Just to see if this was even possible.
Oh.
Right? I didn't give you a question that was impossible, but if they said determine a number between negative 10 and 10 so that you go through 146, I would plug these in and check and say, this is impossible. You're asking me to go through 146, and the highest I ever go is 26. I cannot find a number between negative 10 and 10 that would ever go through that.
So if it's possible, we only look at the x values?
Yeah. Yeah. That's just to check to make sure the question they're asking is even possible. Okay. Most of the time, I'm not going to ask you a question that's not possible. I'm going to ask you one that you can do. Okay. Any other questions on that? All right. Another thought. What if you plugged in a number, okay, like we did here, okay, and you get a negative as your starting y value, and you get a positive as your ending y value? What important number must you have to go through to get from negatives to positives? 0. All right. So what else this tells me, which they didn't ask, but it's very important. If I'm going from negative values to positive values, I guarantee you we crossed the x-axis somewhere. We had to go right through 0 to get from negative to positive. Okay. Any question on that idea? Yeah?
Do you mean the y-axis?
No, x-axis.
So there's x value, so how can you like cross the x-axis?
Because here's your y-axis, right? Let's just put negative 34 down here somewhere. Put a dot somewhere down at negative 34, okay?
You said those were x values then.
These are the x values, negative 10 and 10. Yeah, these are y values.
Oh, okay.
Yeah. So you know what I mean now?
Yeah.
So if you're at negative 34 somewhere, and then you end up at positive 26, this is a straight line, but somehow if you're going to get from here to here, you're going to go through 0 somewhere. Okay? Does everybody see that? Okay, if you go from negative to positive, you go through 0, which is really important because it proves you have an x-intercept. Proves you cross the x-axis somewhere. We're going to skip that one. All right, last part. Okay, last part's probably the easiest part. It's called end behavior. And all that end behavior is if you look at a function, you're looking at what's happening at the very edges of it, okay? Like on the left and the right. Okay, so for example, here's a parabola. I would say the end behavior here is on the left side, it's heading up to infinity, and on the right side, it's heading up to infinity. Here's another function with the same end behavior. It does some twists and turns in the middle, but I would say overall, on the left side, it's heading up to infinity. On the right side, it's heading up to infinity. So there's really 4 different cases you can have. You could have up and up. You could have down and down. Or you could have a cubic, where on the left side, one end goes down, one end goes up. Or reverse it. On the left side, it's going up. On the right side, it's going down. Those are the only 4 cases you can have for end behavior. Okay? And that's what we're describing. Not the twists and turns in the middle. What's happening at the very edges of the function. All right, so let's take a look at y equals x cubed. Let's just get that picture up. There's your graph of y equals x cubed. So if I make it a little smaller, let's put it right there. All right, so the behavior, what's basically happening here, on the left side of this function, it's heading down, and it's going to keep heading down forever. Okay. The y values, okay, on the right side, those are heading up. Right? So basically what we're doing is describing the behavior on the left. Okay, what's happening to the y values? They're going down, and on the right, they're going up. Okay, that's one way to describe what's happening. Okay, another notation that they use to describe what's happening is this notation. It says LIM. It says f of x, and that's pronounced the limit of f of x. Remember, f of x is really just like saying y. So it's saying what's happening to y as x heads towards infinity. Okay? What's happening to y as x gets really, really big? Yeah, it goes up. In fact, it just keeps going up forever. Okay? What's happening to y as x gets bigger and bigger? So does y. It goes up. Okay? How about this one? What's happening to y as x gets smaller and smaller? Goes down forever. Saying these 2 things or these 2 things is exactly the same. I would make sure, though, that you are comfortable with that notation. Okay? So again, the proper way to pronounce it is the limit of f of x as x approaches negative infinity. Okay? Or if you want to word it a little friendlier, what's happening to y as x heads towards negative infinity. Okay, as x goes towards the left, y goes down. Okay, and as I said before, there's 4 basic end behaviors you can have, both up, both down, or one of each. Okay, let's just take this one and write it in limit notation. Okay, the limit of f of x as x approaches infinity. Okay, what's happening to y as x is getting bigger and bigger and bigger? Yep,
It's going towards negative infinity.
it's heading down. Okay. I'll even circle it so you can see this part is described by that. Okay, and then what's happening to y as x heads towards negative infinity? Okay, this is on the left side. What's happening to y as x heads towards negative infinity?
Same thing.
Y is heading down again. Okay? Negative infinity. All right. So if you were going to do all of these, this one would be infinity, infinity, negative infinity, negative infinity. This one would be negative infinity and a positive, and then a positive infinity and a negative infinity. Okay? You'd just be changing these 2 things right here. All right, so let's graph both of these and identify the end behavior. Okay, x to the 4th. It kind of looks like a parabola, but it's a little bit flatter on the bottom than a normal parabola. And what's the end behavior of that? Yeah.
It's going up, right?
Okay, and how would you write it?
Positive infinity, positive.
Well, we either can do this notation, or we have to write out all of that. Let's just use one of these notations. So how would you say it with this?
The first one.
Yeah, the first one. Let's say up, up. Okay. Or if you were going to do it with the other notation, you'd write exactly what you have here, except it would be positive infinity, positive infinity. Okay, before I even graph it, what do you think the negative is going to do?
Yeah, right shape, yeah.
Negative infinity.
Yeah, it's going to take this U shape and it's going to flip it over. All right, so if you just put a negative in, flips it over. Okay, and now we have down, down. Which you could write exactly this. This is exactly what this one is. This is the answer right here. Okay, but I'll just write it again. Down, down. Okay. Any question on that? Yep.
If this is on the test, is it okay if we write it like that, or would you want the other one?
You can write it either way if it's a short answer. If it's a multiple choice, you're going to have to look at how I wrote it. I'll either use this notation, or I could use the arrows. It could be either way. Yep.
Can you write the other notation for the one on the left?
This one?
Yeah.
Yep. So the limit f of x as x approaches infinity. This I get from that. As x approaches infinity, that's the right side. So look at the right arrow. It's going up. Up is infinity. The other one, the limit of f of x as x approaches negative infinity. Negative infinity is the left side. Okay, that's heading towards the left. Look at the left arrow. It's heading up. Okay, and really, we can figure out what the end behavior is without even graphing it. Okay? All you have to do is look at two things. One, look at the highest degree term. Okay? Look at the exponent. If it's even or if it's odd, that basically tells you if they're both going to go up, both go down, or one of each. Then look at the coefficient in front of that term. Okay? If it's positive, that would be up and up if the exponent was even. If the exponent was even and the number in front was a negative, like we did in the last problem, negative x to the fourth, that would be down and down. If you had an odd and the number in front was a positive, the behavior would look like this. Down on one end, up on the other. If you had something like, let's say, negative 2x cubed, it's an odd exponent. The number in front is negative. It's going to be up and down. So it gives you an idea of what it's going to look like before you even graph it. All you're going to look at is that number and that number. Okay, so n is your exponent. A sub n is the coefficient in front. Hey, any question on that? So basically this term right here really controls everything that's happening. Okay, that's called the leading term. And it controls the entire polynomial. Anything else that comes after that might cause little twists and turns, but nothing else can affect the end behavior. Just the leading term. That's the only thing that's important for end behavior. Okay. So the bottom line is if you've got some fancy polynomial, okay, like 3x cubed plus 2x squared minus 8x plus 7, and you want to figure out what's the end behavior, all you have to do is look at this first term. Okay? And that first term models the end behavior. So we call it an end behavior model. Right, so if I give you a polynomial and say, write the end behavior model for this polynomial, all you have to do is write down the leading term. Everything else after it doesn't matter.
Continue with them.
Yep, this will be our last one. Right, so in example 6, it says 2x cubed minus 7x squared minus 8x plus 16. What is the only term there that affects the end behavior? 2x cubed. And 2x cubed, that is the end behavior model. So if I asked you what's the EBM of that problem right there, it's 2x cubed. Okay, let me graph the original and the end behavior model and show you how similar they're going to look. I'm going to show you that all this other stuff doesn't even really make a difference when you zoom out. All right, so 7x squared minus 8x plus 16. Okay, and I'm going to graph just 2x cubed. Now, if I look at it zoomed in, do those two graphs look the same? They don't even look close, right? That's because I'm zoomed in. I'm looking at the small picture. Let's zoom out. Look at the big picture, and they're going to look almost identical. Okay, negative 40 to 40, and negative 10,000 to 10,000. Okay, there's the original, and here's just the end behavior model. See how similar they look? All right, so the end behavior model basically gives you a big picture idea. If you zoom in and look at all the little details, yeah, they're going to be very different. Okay, that's not what the end behavior model does. It gives you a big picture, very simple formula for what it would look like if you zoomed out very far. Right, so the last one, just tell me what would the end behavior model be for example 7? Yep, negative 0.5x to the fourth. If I want a big picture idea of what's happening, graph that and it'll tell you. Okay, and what would the behavior be? It'd be up, up, down, down, one of each. Even exponent, negative, down, down. Even exponent, negative, down, down. Right, so that's the three things in that lesson. So continuity, intermediate value, and behavior.
Do you mind going back to that chart for a second?
Yep, I can put that. Let me put that chart back up. So that's the homework on 161. Okay, so it's definitely less than last night. Just 1 through 5, 9, 10, 12, 15, 16, 21 to 25, and 29 to 31. Okay, I will be after school today if anybody needs extra help. We have our test tomorrow, and don't forget, you can make a reference sheet for this test.